gray box are all different instruments that we actually fly. We set them up in the lab like this for testing and calibration.
Yeah, if we're gonna open one, we can probably open that thing.
So, yeah, can you guys mind maybe just kind of like pointing
Pretending
at
to
a
do
little
things.
bit? And
I know it's hard to do it in a pretend way. So yeah, this one over here is one that we've flown quite a lot. So this is the N201.
Yeah.
This is the N201. And so this has been the one that's actually for the project that we're talking about that we've actually flown. And so you have the pump. So this is how the air gets drawn in. There's an inlet here that would then go outside the airplane, draws the air in through the instrument, and then it actually comes out through the pump. So the pump provides the vacuum power. If we go to the other space, we can open it up and it's a little bit easier to point through some different things.
so it comes in through this
Yeah, so right here. It's
Oh,
right
oh,
here.
there. Okay.
And so the air comes in here, and then in this case it goes through a filter, then to the mass flow controller, then it goes on through this tube into the instrument. It's measured in there, and then the air flows its way out. The other connections here are, this sends chiller fluid through to keep the laser at a very specific temperature and also to keep the whole box at the same temperature, because as we fly around the temperature changes quite a lot, and so you want to keep the instrument at a constant temperature.
And so how do you decide exactly what you're measuring for? Is it always the same thing? Or?
So it just depends on the question and the campaign of interest, right? So the gases we tend to measure are methane, nitrous oxide, carbon dioxide, because we're very interested in them. We'll also measure related gases like ethane, which tells us something about what's happening for methane. So it's really, we're measuring specific gases that we have questions about.
We're asking how the instrument knows which one?
Or maybe how, you decide, what you're measuring for,
Oh, okay.
Yeah, so it's motivated by what our questions
Of course,
are.
yeah, that makes sense.
If you're interested in more air quality, you measure slightly different gases.
And then what is this? The pump just pumps the air out?
It's a vacuum
Okay,
pump. So
okay.
so it draws air. So we have the air when we fly is going about 1.5 liters per minute. It's the flow rate of air. So it's a pretty good flow of air. The instrument measured it at, it's a pressure reduced compared to the atmosphere. So it's at roughly 40 torr, which
Atmosphere
is
like 760.
like 5%. So like 5% of the atmospheric pressure. So it's basically under vacuum, but it's to make the optimal measurement.
And in terms of pulling in the air, is this just kind of hanging out the side of the plane?
Yeah,
thought
we
I had a
don't
picture.
actually have.
I might have sent. Did you get like a bunch of?
I think
Okay, yeah.
It's like a fancier metal tube. It's not just a
Yeah,
loose
okay.
thing.
I might
It's
have a
a,
picture
it's a fancier metal
But
tube.
you're not actually, you have to pull it in, or is that just caused by
No.
No, yeah,
it's,
you pull
it's
it.
drawn by the pump.
the jump? Ah,
Yeah.
gotcha. Of course.
So we can look on the inside of this one. If you're interested. So this is the inside of the instrument. This part is all the computer type stuff, right? So there's a computer. There's also all the electronic controls, the power supply. This box here that we're opening is the optical box, and it contains all the laser and optics and cell where the actual measurements are made.
Do you want to take off the other one too?
We can just, I guess we might as well. Otherwise it looks like a box in a box.
Yeah.
So this is, you can see it's for thermal basically, right?
Mm-hmm.
There's thermal insulation, and then that's even more kind of thermal shielding. So if we need to do an alignment of the stuff in the field, you see there are these holes here.
Mm-hmm.
You can reach through and touch the mirror alignment through the holes without having to take this off. We'll take this off now so you can see what the optics look like.
I forget the people who make it. They call it the fridge box or something.
This?
Like inner box
Oh.
inside the bar. I think it was the fridge.
So yeah, this is the inside of the instrument. So the air goes in here. This is the cell where we make the measurements. And so then the air goes back out that tube that way. This cell has mirrors on both sides. So there's a laser here. The light is collected and sent into the cell. It goes back and forth, so it makes a total path of 76 meters. So it's like 270 or 230
Oh, passes, yeah, 250.
passes through there. And then it goes back and the detector's underneath here. And that's where the detector is.
Wow. So the laser is what's actually detecting.
Yeah, so the laser is designed to hit a specific wavelength for the gas that we're
Uh-huh.
interested in.
Okay.
And it's collected through, and you tune it over a wavelength range where that gas absorbs. And so if there's more N2O present, then the signal we measure at the end has less signal. And that's how we can actually determine
Wow.
that.
Can you motion how air moves through it once more?
Yeah, so let me make sure I'm
Just the
pointing to the right.
inlet.
Yeah. So the air comes in the inlet here. It goes in, down into here. It passes through this cell, and then it exits out through this tube here, and out to the exit.
Great, thank you.
And do you see, say when you're flying over a field, does the measurement change pretty dramatically for short distances? I mean, do you see, large changes just from a few yards, or is it? You understand my question? Like,
Yeah,
is it?
Yeah, there can be very large changes in very
Yeah.
short distances. So there'll be very large spatial gradients, particularly if, let's say, you fly downwind of a large fertilizer plant.
Mm-hmm.
When you get downwind of the plant, you'll have an almost instantaneous huge jump in the signal. And then once you fly far enough that you're no longer downwind of it comes down really rapidly.
Mhm.
So these measurements are made, actually, they're made at 1 hertz, so it's 1 measurement per second. So you have a measurement every second. And it's a unique measurement in some ways.
And so all the data gets put out into
It's collected on a computer, and we have a screen active while we
Okay.
fly. And sometimes it'll even be connected via 4G, so on the ground you can actually watch it in real time as
Oh,
it's
wow.
collected.
And do you write the program where you can actually?
Nope.
No.
No, there are a couple different programs. I mean, some of them our collaborators have put together. For that.
And then did you actually build this?
So
or
this is from Aerodyne. So a company builds this, and then we basically, so they kind of build this box, and a lot of the modifications we make to operate it are related to the pressure control system and the calibration that happens outside of the box, actually.
And so these are all meters.
Yeah.
That is really fascinating.
So yeah, you see, this is a visible trace laser, which is just used for helping to actually set up the alignment, because then this laser is invisible. So we
Oh,
can't. It's in
wow.
the infrared, so it's
Right,
harder to
right.
set up all the mirrors for something in the infrared. So yeah, it gets collected on this. It's like it's a microscope objective mount. It's like a reflective
Uh-huh.
objective that focuses it. It basically makes its way down here, goes to the cell, and then comes back out and onto the detector. There's a couple of subtleties over here. There's a cell that oscillates into the line that has some of the gas of interest, so that you can make sure you know what wavelength you're at. And then there's a thing called an etalon, which lets you know, as you tune your wavelength of your laser, how rapidly are you changing the wavelength. The way we change the wavelength is actually by changing the temperature slightly. And it
Oh, really?
It changes the wavelength that's emitted a little bit. It's very small range.
Mhm.
It's a very small range.
It's like actually relatively simple for being so complex,
Yeah, it looks like this big, intimidating,
Yeah.
complicated thing, but it's a really simple principle, which is that if
Yeah.
there's more of the gas present, our signal goes down, and if there's less, our signal goes up. And then the tricky part is making an accurate calibrated measurement. Like that simple concept is actually really easy. And something like CO2, you can actually set up an experiment that you go buy stuff at Radio Shack and you can measure CO2. It's not that hard. It's hard to measure it with the accuracy that we need to answer our questions. That's where it becomes really hard. And so, yeah, but the principles behind it are actually really pretty simple. It just leverages a lot of fancy looking technology. To get there.
Yeah, and then under like the forces of being in the air, like all these mirrors might like move slightly. That's like things. That's why we have to do all this stuff on outside of the instrument to try to to measure how things are changing that are not actually our signal, and then try to correct for that.
So have you done troubleshooting actually in the air, like having to?
No, you wouldn't want to be messing with the mirrors because you're vibrating kind of. But on the ground, yeah, like in between flights and things like that.
I have done some type of troubleshoot in the air. I actually had, well, we had a problem. I was on flights in the Arctic, and we were at like 500 feet above the Arctic Ocean, and our instrument had a problem and went out. And it was that there was a bad flow meter, and so it turned off the instrument because if it thinks there's no fluid flowing, it will turn off the instrument to protect your laser. But we realized that the meter was broken, the flow was still there. And so we were like replacing the flow meter like while bouncing around on the airplane. So it has happened before. Yeah.
That is fascinating. Cool. Thank you.
Yeah.
Cool. I think
this is very always. It's like there's always all this weird stuff they like. It's like the embarrassing stuff. Sometimes is what looks interesting to a broader audience.
And so how many people are in your department, actually? How many people are,
in my group?
Yeah, in your group.
So I have, right now, there's 4 PhD students, 2 postdocs, so Jenny's a postdoc. And then we have a couple of research scientists that sit with us that work in a federal position. But so we're, depending on one's perspective, we're either quite big or small. Just depends on what background they come from. But there's a decent number of people. So Jenny's been kind of the primary person recently on all the airborne. The group is doing more analysis, satellite data, and analysis work. But yeah, it's fun.
And have you done quite a few international trips, or you gone all over to take measurements?
Yeah, 2 gens and 1. Oh, and then if you count.
So there's even 4 because there was the offshore.
Yeah.
Yeah, which I was. So last year we had a lot of like. On YouTube.
How was the air quality?
I don't think it was particularly good.
Yeah. Well, it's just interesting because you see them tracking, right? Because they're like super zoomed in because they're on the Empire State Building, and they just like zoom out and like you don't know they're on top of it.
Yeah. But yeah, so we have. I'm trying to dig some of that because some of that might be neat. Like
Yeah, definitely. Definitely.
Yeah, I don't think I have that. I know Colin had some videos, but he lost his phone. He dropped it out of there. Over water.
Because the best way to get a good photo is to take the window out. It's not a pressurized airplane.